Today's lesson is on waves. Waves move through space at the same speed, the speed of light. Have we ever had any experience with light or color before? Right, and is this coming from the sun, Marcus?
No, I don't think so.
Okay. How's that light getting to you right now? How's that light getting to you, Marcus?
It's like a straight line. Looks like you're. Yeah, I don't see any ways it would. It's just coming straight down me.
A common misconception for middle schoolers is that light is everywhere and it's not being emitted from a certain object, like the sun would be emitting light. So this is one of the vocab words that I'd like to focus on. Emit. Light is either emitted or how do we see this here? How do we see these different colors that I'm going to show you soon? How do we know that they're there? Are they emitting light? Like reflecting. Very good, Lainey. Reflect. We'll just put emit and reflect. So here's some pictures of these waves. All waves behave in the same way. They don't speed up or slow down. They're always going at the same speed. What is that speed?
Speed of light.
Speed of light. Very good. Uh-oh. It looks like I might be having the same problem as Marcus did.
maybe
It's
the
still
timing works.
recording. It's still recording. Just checking. So we have some different size waves here. What do you think this means? Is there more energy in this bigger wave? We just finished up on a lesson with physics. That's Marcus's camera beeping. Sorry, Marcus.
Oh, it is?
I unplugged it. Okay. And when we drop something from a high point, does it have more energy than if I dropped it down here?
Yes.
Well, we learned that it has the same amount of energy, kinetic energy, potential energy. So if we think about everything's moving at the same speed, the speed of light through space, and we have this great big wave, and we have this little tiny wave, it's going to take a particle, right, going up this big wave and coming down, more or less energy than this wave that's going very fast like that. Picture this as like a building. If this was a building and put a hat on the building, like a skyscraper size wave. And this was the size of a bug, all right? What has more energy, this big wave or this little wave?
The same.
The same? Okay. I'm kind of getting off track here. It's actually the opposite because this little bug, to be going at the same speed as this big building, is moving faster up and down, up and down, up and down to catch up with this big wave. All right. So the emission sources are important to think about as energy traveling. And once they get to an item, they get reflected. So this whole unit is on different ways of communicating information. And I got these from the special ed department downstairs, and students use these in special ed to change contrast on when they're reading so they can focus on the words better. And I'd like everybody to look at one of these. I'll hand them out. And you can put them on your paper there, kind of experiment with them. This is a science class after all. And tell me about the qualities of these different reflecting, do you want purple or blue? I'm trying to get all, how about green? So what's happening to that light, David, when you view through it? Is it blocking out some of that light? What's going on with the light?
I think it might be blocking out some of it, but some of it gets through.
Okay, and would it be blocking out the purple light then?
No.
Everything turns purple, right?
Right, yeah.
So it's letting that purple light through, but it's blocking out or reflecting or absorbing. That's our third word here. Some light gets absorbed as it reaches surfaces. And that's why black things turn hot in the sun. Has anybody ever experienced that, touching black things before? Your head? Okay. So what happens when we intersect these colors? Does it change even more? This would be hues. We got purple and red, green and yellow. What is what's changing when you can go ahead and pass those around? Mix them up. It's a deck of cards.
It absorbs more when you add them on, or reflects more.
Okay. So we get different qualities though, right? Like I started here. The qualities of light can be quantified in size, or we can qualitatively look at these. But you guys can play with these. I've got a ton of these. You can play with these. Qualitatively assess, what's happening with the light. Is it getting blocked out when we put them all together? What is that color when we put up all the colors together?
It's just black. Yeah.
Yeah,
Right.
yeah, it's darker.
Because all the colors would be getting absorbed. I need to write absorbed here. Absorbed. Absorbed. Okay. So quantitatively, when we look at light, red, you guys have to remember this, all right? This is going to be assessed tomorrow. Red is that first wavelength that we see. It's bigger. It's not the size of a building. If this was all the spectrums of light, we have what we call visible light. And that visible light is the colors that we see, right? Name some of these colors. We have red. What else?
Yellow.
Yellow,
Blue,
blue,
green,
green.
orange.
Great. I think you guys are doing my job for me. And there's one more. Violet. Thank you, Lenny. Okay. This is the colors of the rainbow, right? And when we measure red light, it's got a longer wavelength. Okay, kind of like, this is not the wavelength, this is the wave height, the amplitude. But if we had two waves, like this wave here, I'll draw it in a different color so to highlight it. If this was green, which is kind of in the middle of our colors here, we can measure between, what does that look like? What does this wave part look like to you guys? Come up with some describers. What is that?
A hill.
A hill. Come on,
Like a
Marcus.
sand dune.
A sand dune.
Like a noodle?
A noodle. The whole thing is like a macaroni noodle, or
Yeah.
we're going to talk about macaroni later too. He was a great inventor. And then this part, what is this part?
A valley.
A valley,
Yeah.
okay. So that's a different part. That has a different look than this hill or this sand dune. We call this a peak. And this a trough or a valley. All right? We can call that a valley. And then what do we have over here? What's this starting to look like?
Another peak.
Another hill, right? Another peak. So if we measure from peak to peak with a ruler, we'd have to use a very small ruler because these aren't actually the size of buildings, these wavelengths of light. These are more like the size of bugs. We call that an angstrom, right? You need to look at my source here because there's a lot of complicated SI units. We have frequency, how often these waves are getting to us, right? How many waves are in this one? More or less than this one?
More.
More waves, so more frequency. That's expressed as the letter F. Okay, and we have the speed of light, right? Talked about that. All these waves are getting to us at the same speed. Light, like Einstein theorized, is represented by the letter C. Okay, and then since we know that they're all getting to us at the same time, and these little ones are having to move quicker to catch up with this big one, right? There's more wave lengths, right? There's more peaks and valleys in this wave. So that's going to be directly proportional to the frequency. This is also known as the Greek letter nu. This is new information. And I know this is a very complicated lesson. Just bear with me though. I'm almost done. I'm going to move this so we can see better. Or maybe I'll just erase this. Because I think you've gotten the concept that there are different size waves, and those sizes determine how frequent those wave hills are going to appear. All right? So we have wavelength, which is represented by a funny letter called lambda. It's also Greek, but I'll just use W, okay? To try to keep it simple. Everybody smile about that? All right, we have the speed of light. Everything's getting to us at the same rate. And then when we have how many times they're repeating. So that's kind of like for David, we have different pitches, right? So different pitches are different qualities of sound. And if we talked about waves of sound, that's similar to waves of light, right? There's different qualities to these colors. And this is what you need to know for the assessment, all right? So I just introduced a bunch of concepts through direct instruction. I hope the visuals helped out a little bit, and I hope the takeaway is that we can use different transparencies to help color pop a little bit. And I've written into my lesson that there's different ways of seeing the world, right? Through rose-colored glasses. So I brought some different safety glasses, and you guys can put these on if you want.
Both of
Yeah. See, now I can see less blue stuff, I think. Oh no, it's just more green. Now I can see the blue. So the green is absorbing the red and blues. The yellow is absorbing the greens. Try that out if you want, or look through those. All right, I'm done.
Cool.